Hello and welcome back to PC Retro Programmer. In this video we're going to be combining the two line drawing routines that we implemented in previous videos into a single function which can handle both cases. So you might remember that what we have so far is a horizontal-ish and a vertical-ish version of Bresenham's line drawing routine. But we restricted in both cases to lines that were moving down and to the right. So in this video we want to combine the two routines together so that we can handle all cases of lines down and to the right in a single function. But we also want to lift the restrictions slightly. Think about a line that's moving up and to the left. If I draw that line in the reverse direction, it would be down and to the right. So we really already have code for handling this case. All we need to do is just switch the endpoints of the line around. So by the end of this video, what I want to do is to be able to handle all cases of lines moving down and to the right or up and to the left. And the up and to the left ones we'll just handle by switching the endpoints around and using the code that we already have. So once we've done those things, I also have a really nice optimization which I found actually while I was making this series of videos, something that I didn't know previously, and so I'm going to share that with you a little bit later in the video. Let's start by looking at the code that we wrote in the previous video for the vertical-ish case, which was line2.asm, and we already tried to make this as similar as possible to the horizontal-ish case. So in particular, all of the register assignments were the same, and most of the lead-in code was identical as well. You remember what that does is it takes the initial coordinate x0, y0 and computes the x and y parts of the offset corresponding to that point, and also the color and mask values corresponding to that point. So all of that code is the same. The first point at which things are going to differ is the number of iterations. So for a horizontal-ish line, the number of iterations is the number of pixels in the x direction, and for a vertical-ish line, it's the number in the y direction. So this piece of code will actually be different in both cases. So we'll probably move that further down, and then the other things that change are the initial d value here. So this should be minus dx in the one case and minus dy in the other case, and so this piece of code will also be different. And obviously when we compute 2dx and 2dy we change the values of the bp and dx registers, so we don't want to do that before we need those values when computing the initial d. So in the previous video we moved these down here already so that they'd be out of the way and weren't modifying something that we might need to use here. In one case we'd need to use BP, in the other case we'd need to use dx. So it makes sense to move those after that point. But that's already done, and so there's really not very much in the way of changes that we need to make to merge these two functions together. We won't try to merge the main loops because that would just make a complete mess, and it's just not worth trying to make a single version of those. So there will be a different version for the horizontal-ish and vertical-ish cases there. So basically what we're going to do is we're going to end up with an if statement around here somewhere, and it's going to try and determine whether we're in the horizontal-ish or vertical-ish case. Obviously the iterations will be computed after this point, but everything before this point will be the same, and everything after this point will be different depending on which case we're in. So we just have an if statement, and if the code should be in the horizontal-ish case, it'll jump down to the horizontal-ish version of everything from this point, and if not, it will stay here and do the vertical-ish version. Now the other thing that we wanted to do was to deal with upwards moving lines, and the way we were going to do that was to switch the endpoints, and this just means that the line will be drawn in the other direction, so any upwards moving line will become a downwards moving line. Now in order to determine whether we have an upwards or a downwards moving line, we just need to look at dy. So dy is just the difference of the y-coordinates of the endpoints, and so if dy is positive, then it's a downwards moving line, and if dy is negative, then it's an upwards moving line. So basically what we need to do is put an if statement in here that just looks at the sign of dy. If dy is negative, so that we have an upwards moving line, then we just need to switch the endpoints around, and that'll take care of that case. Now the only problem is that there's no point in switching the endpoints after you've started using them, and unfortunately we're using the endpoints much earlier in the function. Up here, for example, we're using x0. So what we need to do is move that computation of dy much earlier in the function. But unfortunately that also creates a problem for us, because dy is currently computed in BP, and of course once you modify BP you lose access to the arguments of your function. So for example, we're accessing the color argument up here, and if we'd computed dy into BP before this point, we wouldn't be able to access this argument anymore. So that's a little bit problematic, and at the end of the day, the solution is to not use BP for dy. So I'm actually going to make a little change to the register assignment. I'm going to switch BP and SI all the way through this code, so that SI gets used for the computation of dy instead, and then we'll be able to move it much earlier in the function. Now SI is the logical choice, because if you have a look where SI is used, it's for the decision variable d way down here. So it's not going to matter if we change this to BP instead. Certainly modifying BP down here is not going to cause us any problems at all. So that's the logical way to handle this, and that's exactly what I've done. I've actually gone ahead and written all of this up, and so we can actually take a look at it in line3.asm. So let's take a look at this thing. Well, I've combined both of the functions, the verticalish and horizontalish cases, into a single function now called CGA line, and the only assumptions left on this one are that it's either down to the right or up to the left. And obviously in the up to the left case, we're just going to handle that in this piece of code by switching the endpoints. Now, I've also exchanged the roles of SI and BP, as you can see from my comments here. These are the other way around, as promised. And I've gone through and exchanged SI and BP all the way through this code. So the only part that doesn't need to have them swapped is this pushing at the start and the popping at the end. That just remains the same, of course. So here is the computation of dy now. It's much earlier in the code than it was before, and you can see that we're computing dy into SI instead of BP now. So the only thing that I do before that now is to compute x1 and x0. So I just read them into registers. I don't actually compute dx at this point anymore, because I don't know yet whether I need to switch these values. But the reason that I read them in from memory here instead of later is because exchanging values in memory is actually quite expensive. Exchanging them in registers is quite cheap. So the earlier we can get these values into registers, the better. So here is the all-important piece of code for exchanging the endpoints of the line. The first thing it has to do, of course, is to exchange x0 and x1. And this is now just an exchange instruction with registers, as I said. Very cheap. So that takes care of the x coordinates if we need to swap them. To swap the y coordinates is a little bit more complicated, because we've already used them in the computation of dy. Now if I switch y0 and y1, that just has the effect of changing the sign of dy. So that's what this negation is all about here. And the other thing that would happen if I switched y0 and y1 is that I end up with y1 in ax instead of y0. Now I could handle that by just reading y1 in again and putting it in ax down here, But unfortunately, reading in from memory is expensive, and so it's much better if we can come up with a way of doing that just with the register values that we already have. So in fact, this turns out to be really easy to do. So if you think about what's in SI at the moment, it's y1 minus y0, and AX has y0 in it. And if you add those two values together, you get y1. So in order to get y1 and AX down here, if we have to switch the coordinates, all I need to do is just add the two values together, and then AX will have y1 in it instead of y0. So in fact, these three lines, which just use registers, are enough to effectively switch the coordinates around. Now, if you haven't already figured it out, this jump if greater than or equal to is the condition that we need if we don't want to execute this switch. In other words, if dy is not negative, then we want to jump over this code, and so that's the condition jump if greater than or equal to. So in other words, if dy is greater than or equal to 0. Now normally you would have a compare instruction here first. You'd have compare dy with 0 and then jump if greater than or equal. But remember from a previous video, I already discussed the fact that if you do an ordinary arithmetic operation on a register, it's as though you had set the flags with a compare with 0 operation. So there's no need to put a compare si, 0 in here. I can omit that because ordinary arithmetic operations always end as though you'd done that. And so that's a little saving as well. So it's just straight into the conditional jump. We jump over this if dy is greater than or equal to 0, because in that case we don't want to switch the endpoints. So that's all that's required to handle that case, and obviously dx still has to be computed, and I just do that down here. It just seemed like a nice place to put that. And a little bit further down here we have the final part of the lead-in code, and this obviously has to be different depending if we're in a horizontalish or a verticalish case. And so that's what these two lines are about. So if we're in a horizontalish case, then dx will be greater than or equal to dy. And so this is what this conditional jump and compare are all about. So it's an unsigned comparison because we're always going to have, at least in the code so far, we're always going to have dx and dy greater than or equal to 0 at this point. And so we can use the unsigned comparison JAE, and if dx is greater than or equal to dy, we're in the horizontalish case, and we'll jump all the way down to the horizontalish code, which is further down below. And if not, we're in the verticalish case, and we'll go straight into the verticalish code. So here's the end of the lead-in for the verticalish code. Here's the verticalish loop, and the end of the verticalish case. And here is the horizontalish case. So here's the end of the lead-in for the horizontalish case. Here's the horizontalish loop, and the end of the horizontalish code. And so that's it. That's all that's required in order to merge these two functions into a single function. So the other thing that I want to discuss is a little optimization that I found while preparing this series of videos. I didn't know about this previously, but it's to do with the part of the code where we multiply y0 on 2 by 80. And I found a really nice trick for this, which I just didn't know about before. So this little trick came about when I realized that it's actually faster to compute 4 times the offset than it is to compute the offset itself. So originally we were multiplying by 80 at this point, and this was done with a total of 6 shifts and 2 adds. So we'd have 4 shifts for multiplication by 16. We'd have an additional 2 shifts to give us a multiple of 64, and then we just add the two values. 16 and 64 is 80. So 6 shifts and 2 adds, and I started to think maybe there's a better way to do that multiplication. And eventually I realized that we can actually multiply by 4 times 80 instead. So 4 times 80 is 320, and that's 256 plus 64. But the advantage is that multiplication by 256 in this case is really fast. So AH is 0, and so multiplication by 256 is just the same as exchanging AH and AL. Obviously, if you move AL into AH, it multiplies it by 256 because you've done an equivalent shift of 8 bits. So that's really cheap. It's just one instruction instead of 4, and then we do the add, and so now we have 256 times y naught on 2. So we just need an additional 64 times y naught on 2. Well, how do we get 64 times? Well, we just divide by 4. 256 divided by 4 is 64. So that's just 2 shifts to the right, and then an add. So this is actually way cheaper. It's really saved us a total of 3 instructions to do this multiplication instead. Now, you might ask, well, maybe that screws up the rest of the offset computation. Is it still just as fast to do the rest of the offset by 4? And the answer is yes, it is. In fact, it's actually faster. So remember that if we're on an odd line, so y naught is odd, we need to add 8192 to the offset normally. Well, now we'll need to add 4 times 8192 to the offset. And 4 times 8192 is 32768, which is just the binary value, which is all zeros except for the top bit. So we basically just need to put a 1 in the top bit of the offset. So we start off with the offset being 0, and we just XOR DI with itself. And of course we need to figure out whether we're in the odd or even case, and so that's just done with the shift right by 1 instruction. Remember, the side effect of that is that the low bit of our y naught value, which is in AX, ends up in the carry. And amazingly, to get that carry bit into the top bit of our offset, there's a single instruction that can do that. This rotate through carry. So it's basically the same as a rotate instruction, just rotating DI, except that it includes the carry in the rotation. So instead of being a 16-bit rotation, it's effectively a 17-bit rotation. And so the carry flag will get rotated into the top bit of the DI register. And that's exactly what we need in the odd case. So this code here actually turns out to be even faster than the code that Jim Leonard had for the 8192 computation. So we're really saving some instructions here as well. Now, the other part of the offset we need is x naught divided by 4 normally, but that now just becomes x naught, so we don't even need to divide by 4 here. So that's another saving. We basically just add it directly to the offset, add x naught directly to the offset. So now we've computed 4 times the offset, much cheaper than we would have computed the offset itself. And the final step is just to shift the offset right twice by 1 bit, which is the same as dividing by 4, and that just gets us back to the value that the offset should have been. So compute the offset times 4 and then just divide by 4 at the end. So isn't that a nice trick? I was really happy when I found that, and I just had not noticed this before. So this sometimes happens when you're writing assembly language programs. If you just focus too narrowly on just the one little bit that you want to make fast, you probably can't find anything faster than what you initially come up with. But if you start thinking about the problem more globally and look at a wider portion of the code, you might come up with some really neat trick like this that enables you to do an optimization of the whole piece of code and makes the whole thing faster. So I've often found that, and it's useful to bear in mind when writing assembly language. Anyway, that's basically it for this code. The only other change that I've made to this program is the main driver function down here. Obviously, we'd now like to test that we can draw both verticalish and horizontalish lines now that we've merged everything into a single function. And it would also be nice to draw a whole bunch of lines so that we can see that the function's working for lots of different inputs. So I changed the main driver program here to do two big loops. So the first loop is going to draw a bunch of verticalish lines, and essentially it's going to start each line at 0, 0, and it's going to finish at an x coordinate that's going to change from 199 down to 0. So there'll be 200 lines in total. The y coordinate will just stay at 199 on the bottom of the screen. So this is going to basically fill out a triangle shape as the x coordinates of the endpoint change, and then we'll see a total of 200 lines drawn filling up this triangle. So then I do a second loop, and this is going to draw a bunch of horizontalish lines. And so this one is going to also start all the lines at 0, 0, but now the y coordinate is going to move from 199 down to 0, and the x coordinate is going to stay fixed at 199. So these are all horizontalish. So this will enable us to give a little bit better test than we had in previous versions. So let's save this and exit, and we'll build this. So assemble and link. And now we can actually run it and see what happens. And this will actually allow us to see how fast our line drawing is, because now we're drawing basically 400 lines. So let's run it. And you can see that was, what, a second, maybe 2 seconds, something like that. So we're really drawing quite a few hundred lines a second on this 286 machine. And everything's filled in perfectly. So it looks like all of the lines were drawn correctly, which is great. And just to check that it does actually exit the DOS when I press a key, and it seems to be all functioning. So now we have basically half of all the possible cases for lines, and in the next video we'll show how to draw the other cases that we haven't dealt with yet.